Alright, hello everybody. This is the video for the AMATYC SML competition round 1 from fall 2024. There are 20 questions here, all multiple choice, and we're going to go through all 20 of them. So let's just go ahead and get started. So starting with number 1, we have 1 BTC. Presumably this is Bitcoin, but we have 1 BTC as worth $62,000. And 3 ADA are worth $1.05. How many ADA are 2 Bitcoin worth, rounded down? Easiest way to do this is to figure out first how much 2 Bitcoin is worth. You get that by doubling the 62,000, so that would be 124,000. And figuring out how much 1 ADA is worth. You get that by taking $1.05 and dividing by 3, which gives you 35 cents. If you divide these two quantities, you get 354,285.7, but we're rounding down. And that's really it. That's 2 Bitcoins worth of dollars divided by 1 ADA's worth of dollars. That gives you Bitcoin per ADA. All right. Question 2. Ali and Brenna play a game. A fair coin is flipped repeatedly until either there is a head followed by a tail, in which case Ali wins, or there are 2 consecutive tails, in which case Brenna wins. What is the probability that Brenna wins this game? So a heads then a tails means that Ali wins. And a tails then a tails means that Brenna wins. Well, let's think about the possible ways for Brenna to win. It's easy. If the first 2 flips are tails, then of course Brenna's going to win, right? Otherwise, the first 2 flips start like one of these things. Heads, 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 tails, or tails, heads. These are the only other 3 starting states for the first 2 flips. Clearly, HT corresponds to an Ali win because that's Ali's win condition, HT. However, if we start with HH, then eventually we're going to hit a T, whatever the first tails is of the game. And then Ali wins right then and there. There's no chance for Brenna to get that second tails that she needs. Similarly, if we start with TH, then you're going to have HHH all the way to whatever the next T is. Maybe there's 1 H, maybe there's 20 H's in between. That doesn't matter. Because once you hit another T, then Ali gets his win condition again. All right. And so in these 3 starting states, Ali wins, but here Brenna wins. And these are all equally likely, which means Brenna's probability is 1/4. All right, moving to question 3. A point AB is a lattice point if both A and B are integers. A lattice point is called visible if the line segment from 0, 0 to the point does not pass through any other lattice points. Which of the following lattice points is visible? And then we're given 5 different possible points here. Okay. Oops. Let's go ahead and use our lines here. Okay, so here's our points, or our grid here. And we have the following. Our point's going to be somewhere out here. So let's take, for example, 2814, just as a guess. All right. What you may notice is that the slope of this thing is 1/2. But what that means is that for every 2 we move horizontally, we move 1 vertically. So that means, for example, the point 1, 2 is going to be part of this line. Same with 2, 4, 3, 6, 4, 8, etc. Right? Oops, apologies. That should say 2, 1, not 1, 2. So flip that. 2, 1, 4, 2, 6, 3, 8, 4, etc. So that's not going to cut it. Similarly, 2816, 2818, and 2821 run into the same issue. And the way this ends up working, let's look at 2818, for example. The slope is 18 over 28, but this reduces to 9 over 14. This means that the point 14.9 exists on this line, because this, again, is a slope of 9 over 14. So what this boils down to is, if I put the two numbers into a fraction, will it reduce? The actual terminology for this is coprime, or relatively prime. The only way that this will work is if the two numbers are coprime. In other words, if they have no common factors, and if you put them into a fraction, they would not reduce. 2815 is the only such point. 28 and 15 have no common factors, and so that fraction will not reduce. All right, moving on. Question 4. How many integers n, ranging from 0 through 2024, have the property that they can be written as a difference of non-negative integer powers of 2? So, for example, 2 to the 7th minus 2 to the 4th gives you 112. So 112 would be part of this set. Well, of course, 0 can be part of this set, right? 0 is, I don't know, 2 to the 10th minus 2 to the 10th. I'm using 10 facetiously. You can use any number there, right? But 0 definitely works. Now, the other numbers, 1 through 2024, only way you can get them is if the two numbers are different. The difference of two numbers is different. Specifically, the first one needs to be bigger than the second one. Otherwise, you get a negative number. So rather than looking at the numbers themselves, let's look at the powers. For example, 7 and 4. Right? If I look at the powers 7 and 4, this gives me 112, as the example shows. I could do a different one. I could do like 9 and 3. This would give me 2 to the 9th minus 2 cubed, right? 2 to the 9th being 512, 2 cubed being 8, so this would be 504. 504 would also be part of this. All right. So the reason I bring it up this way is because rather than looking at these numbers, I'm going to look for these pairs. I'm going to ask how many pairs give me the result between 0 and 2024, specifically 1 and 2024, because we've already counted for 0. All right. Now let's think of it this way. If you start rattling through the powers of 2, you'll notice a few things. You'll notice that 2 to the 10th is 1024. You'll notice that 2 to the 11th is 2048. And you'll notice 2 to the 12th is 4096. Right. If you take 4096 and subtract off 2048, 1024, or any of the numbers that are smaller, your result is going to be too big. It's going to be bigger than 2024. So 2 to the 12th cannot be part of this. And so we need to restrict our search to 2 to the 11th and lower. And this is where the nice trick comes in. The possible powers of 2 are 2 to the 0, 2 to the 1, 2 to the 2, all the way up to 2 to the 11. Oops. And what we're doing is we're choosing 2 of the numbers. And the number of ways to do that is 11 choose 2. Right? You go through 11 choose 2, you get 55. Right? Nope, not 55. And not 11 choose 2. Apologies. There's actually 12 numbers here. This is 12 choose 2. Right? 0 through 11, there's 12 numbers. So 12 choose 2. There we go. That's 66. Now, not all of these work. For example, 2 to the 12th minus 2 to the 0 is 2048 minus 1, which is 2047. That's still too big, right? In fact, if you subtract off 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4, you get numbers that are too big. Specifically, you get 2046, 2044, 2040, and 2032. But once you subtract off 2 to the 5th, 2048 minus 32, that's 2016, and that does work. So these 5 pairs, 12, 0, 12, 1, 12, 2, 12, 3, and 12, 4, fail. Right? So we need to subtract 5. Now we get 61. 61 is not one of the answers. However, remember, 0 is also a viable answer. And this method didn't account for that. So we need to do plus 1 to get 62. All right. Question 5. By placing 3 sum, pluses, or differences operations within the string 1, 2, 3, 4, 5, 6, 7, 8, 9, a number of different results can be achieved. For example, 123 plus 456 minus 78 minus 9 is 492. And 12 plus 3, 4, 5, 6 minus 7 plus 89 is 3,550. So these are 2 possible outcomes. If you do A plus or minus B plus or minus C plus or minus D equals 24 in such a string, what is the value of C? Right? So ideally, we're going to place pluses and or minuses, 3 of them, somewhere in this string to get 2024. Now the problem gives us a really nice clue. And that is all 5 answers are single digits. So C is a single digit number. That's given to us from the answer choices, which is kind of crazy. So let's think about this. Let's go through some of the extreme possibilities. Let's look at A equals 4. If A, or A being 4, so C equals 4. If C equals 4, what am I looking at? I've got my numbers 1, 2, and 3, and this gives us A or B. Plus or minus 4, plus or minus 5, 6, 7, 8, 9. Here's C, and then this number is just D. And this is where the crux of the argument comes in. That value of D is much too large. Whether I put a plus or a minus there, that 5-digit number of D is going to ruin it. We can't get to 2024 if one of our numbers is 56,000. So 4 is not going to work. Similarly, if I look at C equals 5, 1, 2, 3, 4 is split between A and B. So there's a plus or a minus somewhere in there. But then you get plus or minus 5, and then you get plus or minus 6, 7, 8, 9. Even in the best case scenario, 6, 7, 8, 9 is still too big. You could subtract off 1, 2, 3, 4, but you're still around 5,500. That's still too big for 2024. So C equals 5 is going to fail. All right, similar argument. Let's check the other ends because it feels like our answer probably should be somewhere in the middle here. Let's check C equals 8. Well, we have 1, 2, 3, 4, 5, 6, 7. That's going to be split between A and B. And then we have 8, and then we have 9. So 8 and 9 really don't affect the scale. They don't affect the magnitude of this all that much. So the question is, can I use those first 7 digits, split them into 2, and get somewhere in the ballpark of 2,000? Best I can really do is 1, 2, 3, 4 plus 5, 6, 7. And then plus or minus 8 plus or minus 9. But this is still going to fail. Right? You add those 2 numbers together, you get 1,801. That's not quite big enough. It's closer, but it's not quite there. So 8's not going to work. And then for C equals 7, we've got 1, 2, 3, 4, 5, 6, plus or minus 7, plus or minus 89. And again, 1, 2, 3, 4, 5, 6 is in the ballpark of, or is what A and B needs to be. So again, can we get near 2,000 by splitting up 1, 2, 3, 4, 5, 6? And the answer is not really. The best you can really do, maybe you can try 1, 2, 3, 4 plus 56. And then maybe add in the 89 as well, but that's not going to make it. You could also try like 1, 2, and then 3, 4, 5, 6, but that's going to be too big. So that's not going to work. So it seems like C equals 6 has to be our answer. And let's go ahead and check that. I'm going to put that in our right here. If we check C equals 6, same logic. We have 1, 2, 3, 4, 5. And then we have plus or minus 6, plus or minus 789. And you can go through trying to split 1, 2, 3, 4, 5 into A and B, and you're going to end up here. 1, 2, 3, 4. And then minus 5, plus 6, plus 789. 1, 2, 3, 4, and 789 get you very close to 2024. Specifically, I believe it gets you 2023. So these two numbers give you 2023. And so this gives you 1. And that gets your answer. So C equals 6 for this one. All right. Question 6. How many pairs of positive integers A and B with A less than B have 24 as the least common multiple of A and B? And you get 2, 4, 6, 8, and 10. Honestly, you can start rattling these off, right? For example, we know that 124 is going to work, right? The least common multiple of 1 and 24 is going to work. In fact, if you look at the number 24 and you pair it with any of its factors, you're pretty much set. You're going to have 2 and 24, 3 and 24, 4 and 24, 6 and 24, 8 and 24, and 12 and 24. Right? All 7 of these work. That means 2, 4, and 6 cannot be our answers. So the question then becomes, can we find any more? Well, we should find at least one more. And you can go through it, and you can get 3 and 8 should work. Right? That's a good split of the factors. So 3 and 8 work. You should also be able to get something like 6 and 8, right? As well as 12 and 8. Although I should switch those. That should be 8 and 12, according to the stipulation that A is less than B. And that's 10 right there, so the answer has to be 10. All right. Moving on. Question 7. A sequence Sn is formed where the nth term of the sequence is the nth whole number whose representation in binary contains exactly 2 ones. The first 2 terms of the sequence are S1 equals 3, which is 1, 1 in binary, and S2 equals 5, which is 1, 0, 1 in binary. The question is, what is S of 50? All right. So let's think about, just as an example, what would happen if we had 5 digits in our binary number and we're allowed leading zeros here? So just for the sake of argument, if we had 5 digits in our binary string and we're allowing lead zeros. So for example, this is perfectly allowed, right? This would correspond to the number, 10? That would correspond to the number 10. Right? Or something like 1, 0, 1, 0, 0 would correspond to 20. 1, 0, 0, 0, 1 gives us 17. There's a whole bunch of this. Right? In fact, there are 5 choose 2 of these, which is 10. 10 of these different possible strings. And this ranges all the way from 00011, which is our 3 from the original example, out to 11000, which is 24. So there are 10 numbers between 3 and 24. Now, that tells me that 24 is S of 10. It's the 10th number in our sequence because it is the biggest with only 5 digits, right? And there are 10 of those numbers. That's not enough. We need S of 50, so we need more digits, right? This was just an example. If we went to 6 digits, that would give me 6 choose 2, right? And 6 choose 2 is 15. Yeah, that ranges all the way from 00011, which again is still 3, to 110000, which is 48 in binary. All right, so this is S of 15. We still need more. In fact, I need to find a number such that that number choose 2 surpasses 50. All right. And we kind of alluded to that earlier in a different problem. If we go to 11 digits, then we're looking at 11 choose 2, which is 55. Right. That means the following number, 1, 1, and then 9 zeros, 0, 0, 0, 0, 0, 0, 0, 0, 0. All right. So whatever this is in decimal form, in base 10, is S55, right? So this gives me 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, and 1024. So this is 1024 plus 512. So 1536. This is S of 55. So this is too big, right? 1536 is too big. That also immediately reduces us to the first 3 answers. But we're almost there. The next number, or the next smallest number that only has 2 ones in its binary expansion, is 101, 0, 0, 0, 0, 0, 0, 0, 0. All right, this is going to be S of 54. And then the next one is 1001, 0, 0, 0, 0, 0, 0, 0, 0. This is 53, 52, 51, 50. All right. So we're going to have 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. This is the 50th number. This is S of 50. All right. This is 1024 plus 1, 2, 4, 8, 16, which is 1040, which is B. All right, moving on. Question 8. Suppose T of T is 125 e to the negative kt plus 75, gives the temperature in Fahrenheit of a cup of coffee T minutes after it is poured. If the lid is off, K equals 0.1. If the lid is on, K is 0.02. Let T off and T on be the time it takes in minutes for the coffee to cool to 150 Fahrenheit with the lid off or on respectively. What is T on divided by T off? All right, I'm not going to worry about the whole on and off thing yet. I'm just going to solve for T in terms of K. So we'll have a starting temperature. It's easy enough to show that the starting temperature when T equals 0 is 200. That's not super important here. What we need to solve for is 150 equals 125 e to the negative kt plus 75. And I'm just going to go ahead and solve for T. It's just a little bit of algebra here. So we get 75 equals 125 e to the negative kt. 75 divided by 125 is 0.6 or 3/5. So this is e to the negative kt. So negative kt is equal to the natural log of 0.6. And so t is equal to the negative natural log of 0.6 divided by k. So depending on what k is, either 0.1 or 0.02, this is going to be the amount of time it takes for the coffee to cool. So what are we looking for? We're looking for T on divided by T off. This should be negative ln of 0.6 divided by the K for on, which is 0.02, divided by negative natural log 0.6 divided by 0.1, which is the K for off. You can use your calculator here, but the nice thing is that these just cancel. And so this ends up being 0.1 over 0.02, which is 5. Intuitively, this makes sense. The coffee should cool or take longer to cool if the lid is on, which means this ratio should be bigger than 1. Right? It should be longer for on versus off. So the fact that you get 5 as an answer makes sense. All right, question 9. Consider a binary operation, star, on the integers, which is associative, commutative, and distributive over addition, which means that a star b plus c equals a star b plus a star c. If 3 star the quantity 4 star 5 equals 10, find 4 star the quantity 5 star 6. All right, let's start here. 4 star the quantity 5 star 6. This is associative, which means I can move parentheses around. Specifically, I can say that this is 4 star 5 and then star 6. That's from associative. Commutative means I can reorder the numbers in which this is written. So this is equal to 6 star 4 star 5. That's commutative. Now 6, of course, is just 3 plus 3. Sorry, my pluses and my stars look a little similar. In fact, I'll color code them for you. The red ones are the stars. And so we can distribute, because of the distributive property over addition, I can distribute. And technically this is also a bit of commutativity as well. I'm going to skip that part, it's not that big of a deal. So we have 3 star 4 star 5 plus 3 star 4 star 5. These are both 10. And that's 20. Moving on. Number 10, the knights and knaves problem. So 3 people, X, Y, and Z, are in a room with you. One is a knight. Knights always tell the truth. One is a knave. Knaves always lie. And the other is a spy, which may lie or tell the truth. Z says, or X says, Z is a knave. Y says X is a knight. Z says I am the spy. Which of the following correctly identifies all 3 people? And we're given a number of options, as well as impossible to determine from the given information. Okay, so let's break this down. What I really like is looking at Y here. And the reason I like looking at Y in this particular version of this problem is that Y says X is a knight. If Y is telling the truth, then X is also telling the truth, because X would have to be a knight. So let's see. If Y is true, right? What does that tell me? I'm going to make a little grid. I'm going to say X, Y, and Z. And I'm going to say knight, knave, and spy. So if y is telling the truth, that means x is the knight. Because that's what y said. Okay, so these can't hold, and these can't hold either. Well, if x is the knight, that means x's statement, that z is the knave, is also true. So z is the knave. That makes y the spy. All right? So y could be telling the truth or not. That's fine. X is telling the truth. That z is a knave. That's verified here. And then z said that they were the spy. That was a lie, which is a good thing because z is the knave. All right? So according to this, if y is true, if y is telling the truth, then x is the knight, z is the knave, y is the spy, which is answer D. Now, we're not quite done yet. Because maybe if y is lying, we get another solution that is also viable. We don't know that for sure. So let's check. If y false. So if y is lying. I'm going to make my little table again. X, Y, Z. I've got knight. I've got knave. And I've got spy. Okay. If y is lying, that means y isn't the knight. That would be illegal for knights to lie. Also, if y is lying and states that x is the knight, that means that x can't be the knight. So z is the knight. But z said he was the spy. If z is the knight, that would have to be true. But then z says I'm the spy, so that would have to be true, and you end up with conflicting. Right. Specifically, you get that z would have to be both the knight and the spy, and that doesn't work. So our first solution is good, and our answer has to be D. Moving on. Question 11. In triangle ABC, AB plus AC is 31, AC plus BC is 27, and AB plus BC is 38. Find the area of ABC. This one comes down to knowledge of formulas. And there's a very famous formula called Heron's formula. Surely there are other ways to do this problem, but they're much longer and much more tedious. I'm not trying to do any of that. I want to do Heron's formula, which is a way to find the area of a triangle if you know all three sides. So let's suppose you have a triangle. And that triangle has sides X, Y, and Z. We're going to define S as x plus y plus z over 2. This is called the semi-perimeter, and that's because it is half of the perimeter. All right, semi-perimeter S is half of the perimeter. If that's true, if we define S in that way, then Heron's formula is the following. The area of the triangle is the square root of S times x minus x times s minus y times s minus z. So if we can find x, y, and z, then we're done. Well, we can say that AB is x. We could say that AC is y. That makes this y. BC would be z. X is AB, BC is z. So what do we have? We have that x plus y is 31. Y plus z is 27, and x plus z is 38. So we're going to find out x, y, and z from this, and then plug it into our formula. There's a number of ways to do this. There's a whole bunch of different fun ways to do this. I like adding all three of these together. Because if you add all three of these together, you get 2x plus 2y plus 2z, which could be useful in finding our s value, equals the sum of these three numbers. The sum of these three numbers is 96. So that tells you that x plus y plus z is 48. Right? So we'll use that for our semi-perimeter, or our full perimeter, so we'll divide that by 2 again. But if we go back to the original first equation, x plus y being 31, and x plus y plus z is 48, that means z has to be 17. Because you need those 3 numbers to add to 48. Similarly, we get that x is 21, and we get that y is 10. You need the numbers to add up to 48 in all 3 equations. And so, you also get that s is 24 because you divide the 48 in half, and we have the 4 numbers required for our formula. So the area is the square root of 24 times 24 minus 21, which is 3. 24 minus 10 is 14, and 24 minus 17 is 7. You can obviously plug this into your calculator. You can do some shenanigans with prime factorizations if you want to try to do it this way or simplify that way. What this ends up being is 84. And so you get 84 as your answer. Moving on. Question 12. A 3-digit number is to be typed into a system manually, which is also known as transcribing the number. If a digit is transcribed incorrectly, then there is a 90% chance that the next digit will also be transcribed incorrectly. Otherwise, there's only a 2% chance that a given digit will be transcribed incorrectly. Let P be the probability that a given 3-digit number has exactly 1 wrong digit. Which of the following is true? And we get a number of different ranges for the possible values of P. All right, well, there's only 3 possible ways for this 3-digit number to have exactly 1 wrong digit. The wrong digit can be first, it can be second, or it can be third. So we're going to look at all 3 of those cases separately. I'll go ahead and color code this. Oops. All right, so these are the 3 numbers. So red means wrong, black means right here. So these are the 3 possible ways. So in the first case, in the first row, the probability that the first digit is wrong is only 0.02. There's only a 2% chance that this is wrong. But then the second number, the probability that it's wrong is 90% because the first one was wrong. But we need this to be correct. So it's actually 10% that this is correct. And then the third one, we don't need to worry about the 90-10 anymore because the second one was correct. The third one, probability of also being correct is 0.98. It's the opposite of that 2%. So that's the probability. When you multiply these together, you get the probability that the first one was wrong and the last 2 are correct. We're going to do a similar thing for the second and third possibilities. So in the second possibility, the probability that the first digit is correct is 0.98. And then the probability that the second one is wrong is 0.02. And the probability that the third one is correct, well, it being wrong is 90%, kind of just like the first example. So this one will be 0.10. So we'll multiply these together as well. And then the third one is 0.98, 0.98, and then 0.02. Using the exact same sort of logic. And what you end up with, when you multiply these 3 together and then you add their results, I ended up with 0.023128. Just use a calculator for that. It's really just a matter of multiplication and addition. And so our answer should be C. All right, moving on to question 13. Honestly, this showed up multiple previous tests and has never been my favorite question. This is always the question that gets weirdest. The equation a to the fourth plus b cubed plus c squared equals 2024 has a unique solution in positive integers. Find a plus b plus c for this solution. All right, and the possible answers are all between 48 and 52. All right. Okay. Honestly, the easiest way to do this is probably to rearrange the equation to look like this. A to the fourth plus b cubed equals 2024 minus c squared. And start rattling off different possibilities of c. Okay. So, one thing that we do know, and that can help us shore up our possible answers here, is that 45 squared is 2025. Which means that c has to be less than or equal to 44. And it's probably going to be easiest to find solutions if you start from the largest numbers and the most restrictive possibilities and work your way down. So you would start with c equals 44. So 2024 minus 44 squared. Plug that into a calculator and you're going to get a pretty small number. What you're going to get is 88. And so we're sort of doing a brute force here. What you're looking at is a to the fourth plus b cubed equals 88. There are not many possible things for you to check. And you can check that this doesn't work. So then you move down to 43. And that doesn't work. And you move down to 42, and that doesn't work. And you move down to 41, and that doesn't work. And then you get to 40. 2024 minus 40 squared is 424. And so we are looking at the following equation. A to the fourth plus b cubed equals 424. All right. Now that and this is probably how you'll want to check the A's and B's for the other cases as well. A to the fourth gets pretty big. And gets pretty big pretty quickly. So check A equals 1. B cubed would have to be 423. That's not going to work. 423 is not a perfect cube. Check A equals 2. 2 to the fourth is 16, so we're looking at b cubed equals 408. That's not going to work either. And then you get to a equals 3. All right, 3 to the fourth is 81. And what you find is that b cubed is 343. And 343 is 7 cubed. So our solution is A equals 3, B equals 7, and C equals 40 for a sum of 50. This problem is absolutely a calculator problem. It's testing your ability to go through a bunch of cases quickly using a calculator and being efficient. Right? There are algebraic techniques that you can use, but they're not super clean. You just kind of have to work your way through it. All right, moving on. Question 14. Two lines, y equals mx plus b and y equals bx minus m, where m and b are non-zero, are perpendicular. Find the x-coordinate of their point of intersection. All right, well, if you know that they're perpendicular, that means you know their slopes are negative reciprocals of each other. In other words, m equals negative 1 over b. Or b equals negative 1 over m. I'm probably going to use that second one because all of my answers are in terms of m. So I want to get rid of b. So we know these two things. The x-coordinate of the point of intersection is when the y's are equal to each other. And so we're going to go ahead and set them equal to each other. mx plus b equals bx minus m. I want to solve for x, and I want b to equal negative 1 over m. So I'm going to say mx minus 1 over m equals negative 1 over mx minus m. Now, ultimately, the goal is to get x by itself, but to clean this up a bit, I'm going to multiply everything by m. So this will be m squared x minus 1 equals negative x minus m squared. All right. I'm going to move the x's to the left side and the constants or the non-x's to the right. So this will be m squared x plus x equals 1 minus m squared. Factor out the x and divide, you end up with x equals 1 minus m squared over 1 plus m squared. And that is answer choice E. Okay. Question 15. How many of the following statements are true? 1. I'm just going to go through them. 1. 0 is an even integer. Yes. Even integers can be written as 2 times a whole number. And 0 is 2 times 0. 2. X cubed plus 27 equals 0 has exactly 3 distinct solutions in the complex numbers. That is true. Right? One important thing about polynomials is that whatever the order of the polynomial is, so in this case 3, so order 3, the highest exponent, is going to be how many solutions it has in complex numbers. The only question is, are all 3 of these distinct? And the answer is yes. Right? Interestingly enough, x cubed plus 27, if you graph in the complex plane where these are the real numbers and these are the imaginary numbers, will form a nice little equilateral triangle. Those are the 3 complex solutions. 3, the union of the set of rationals and the set of irrationals equals the set of real numbers. That is true. Irrationals are just real numbers that aren't rational. So this is true by definition. Rational and irrational numbers are distinct from each other, and irrational just means not rational but real. Right. That's true. And then 4, given 2 distinct real numbers a and b, we can always find a real number c such that a less than c less than b. This is false because they don't tell us that a is less than b. Right? We could have like a equals 10 and b equals 4. You're not going to have anything greater than 10 and less than 4. So there's 3 correct statements here. All right, question 16. In the system of equations, xy plus z equals 105 and x plus yz equals 107, how many distinct integer values of y does the system have a solution in the integers? Okay, the way I ended up solving this is the following. I took these 2 equations and I subtracted them. Specifically, I took the 107 equation minus the 105 equation. So we get that x plus yz minus xy plus z equals 2. Right? It's 107 minus 105. And I'm going to go ahead and rewrite the left side and try to do some factoring. So we have x plus yz minus xy minus z equals 2. I'm going to group the y terms and the non-y terms. So I have x minus z, and then I have plus yz minus xy equals 2. I'm going to factor out the y from the second one, and actually I'm going to factor out a negative y, and I'll explain why shortly. X minus z minus y, and this is why I'm doing the negative. If I factor out negative y, negative xy just becomes positive x, and yz becomes negative z. And now I have a factorable thing, x minus z, x minus z. So this is x minus z and 1 minus y equals 2. Now, why is this helpful? Well, the system is specifically looking for solutions within the integers. And if I have solutions within the integers, that means both of these quantities are integers themselves. Specifically, 1 minus y has to be an integer factor of 2. Right? So 1 minus y could equal 1 or 2. It could also be -1 or -2. But it can't be anything other than those, because then x minus z wouldn't be an integer. And so solving for y, we end up with the following possibilities. Y being -1, 0, 2, or 3. Now, these are the 4 possible values of y, but these are not necessarily all going to work. We have to go back to the original system to determine which of these actually make things make sense. So I'm going to copy this down here so that we can see it more readily. So we have xy plus z equals 105. And we have x plus yz equals 107. We're just going to check all 4 possibilities. So if y equals -1, I see -x plus z equals 105, and x minus z equals 107. Here's the issue. These two expressions are negatives of each other. That's x minus z and z minus x. But the two results are not negatives of each other, so this fails. Okay. -1 doesn't work. Let's try y equals 0. Well, this actually works out really nicely. If you set y equals 0 back to the original, which I'll circle so we don't lose it. If we set y equals 0 back to the original, that just gives me z equals 105 and x equals 107. Sure, that's perfectly fine. So 0 is great. What about y equals 2? I'm looking at 2x plus z equals 105, and x plus 2z, I apologize, my 2's and my z's look kind of similar, 2z equals 107. Well, you can solve this system of equations. It's not insane. Do so. One thing that I like to do here is add the 2 equations again. You get 3x plus 3z equals 212. This is not going to have integer solutions because trying to divide by 3 gives you a fraction. That doesn't reduce. 212 over 3 is not a reducible fraction, so you can't have 2 integers that add up to a fraction. This is going to fail. So 2 doesn't work. And then 3. Y equals 3. We have 3x plus z equals 105. And we have x plus 3z equals 107. All right. You can add them together again. You get 4x plus 4z equals 212. This actually does work. 212 is divisible by 4, so you get x plus z equals 53. And if you take this equation and you subtract it from each of the 2 original equations, then you get the following. 2x equals 52, and 2z equals 54. So x is 26, and z is 27. So you get x equals 26, z equals 27, and y equals 3. The only 2 ones that work are 0 and 3, which means my answer is, is 2. All right, moving on to question 17. if the square root of 21 minus 20i equals a plus bi, then find the absolute value of a minus b. This question is actually a lot easier than its placement implies. The fact that it's question 17 makes it seem like it's really hard, but it's actually really not, as long as you know what I is. I is the square root of negative 1. And so what I'm going to do is take this equation and square both sides. All right, and what I'm going to get is 21 minus 20i equals a plus bi squared. My next step is going to be to FOIL this out. So I have 21 minus 20i equals a squared plus 2abi plus b squared I squared. Again, remember, I is the square root of negative 1, which means that I squared is negative 1. So I'm going to take this equation here, and I'm going to group it into its real parts and imaginary parts. I have 21 minus 20i equals a squared minus b squared plus 2abi. This a squared minus b squared needs to be 21, and this 2ab needs to be negative 20. So that tells me that a squared minus b squared is 21, and 2ab is negative 20, or ab is negative 10. Easiest way to solve from here is just to go through factors of negative 10. So think negative 1 and 10, negative 2 and 5, negative 5 and 2, negative 10 and 1, and see if any of those work with the first one. And it turns out that it does. Right. What you end up with is a being 5 and b being negative 2, or a being negative 5 and b being positive 2. Both of these work, right? Both of these work. The square roots with I kind of get a little bit strange. Square roots are actually not necessarily unique in a lot of cases once you start talking about complex numbers. The good news is the thing that we're looking for is the absolute value of a minus b. That's just the distance on the number line between a and b. And in both of these cases, the absolute value of a minus b is equal to 7. That's probably why they wrote it that way. So our answer is 7. Question 18. Moving on. Two of the solutions to the equation 2x minus 5, x minus 2, x plus 1, x plus 2 equals 20 are single-digit integers. Thank you, problem writers. And the other two can be represented in the form a plus or minus root b over c, where a, b, and c are integers, c is greater than 0, and b is prime. Find a plus b plus c. Okay. So, the problem tells us that two of these solutions are single-digit integers, which honestly means I should just start plugging in single-digit integers and see if I get viable answers. I don't even need to multiply things out, right? Now, that being said, if I do multiply things out, one of these is going to become apparent, but if you check through some single-digit answers, just start with 0. 0 is always the easiest one to start with. And if you start with x equals 0, you get negative 5, negative 2, 1, and 2 is 20. That is 20. That works. X equals 0 is one of these. So x equals 0 works. And then you can move on. You can say x equals 1, x equals 2, whatever. As you go, x equals 3 gives you the following. 1, 1, 4, 5. It's 20. So x equals 0 and x equals 3 are the two single-digit integers that are solutions. So this is what we're going to do. We're going to keep that in mind. I'm going to multiply this entire thing out. into a big, nasty quartic polynomial. The good news is we'll know exactly what to do with it after we've done that. So let's take 2x minus 5, x minus 2, x plus 1, x plus 2. I'm going to get everything on one side, so I'm going to say minus 20 equals 0. We tend to like to do that with polynomials. I'm just going to multiply it out. So let's go ahead and multiply out these guys. That's going to give me 2x squared minus 9x plus 10. And then if I multiply out x plus 1 and x plus 2, that gives me x squared plus 3x plus 2 minus 20 equals 0. And I'm going to keep going. I'm going to multiply out this entire thing. And so we have, when I multiply this out, I'm going to skip the algebra and just go straight to the quartic. We have 2x to the fourth minus 3x cubed minus 13x squared plus 12x plus 20 minus 20 equals 0. All right, so this part right here, up to this 20, is what happens when you multiply. It's all the big foiling out, all right, the big distributing, expanding, so to speak. Okay, of course, the 20s cancel, and so I'm left with this equals 0. And I can factor out an x. We kind of knew that already. X equals 0 is a solution. So I can factor out an x, and I'm going to ignore it for now. 2x cubed minus 3x squared minus 13x plus 12 equals 0. It's generally bad form to divide by x, but if you already know x equals 0, then you no longer need that fact, so you can divide it out. The other one we know that works is x equals 3. And what we're going to do is actually divide this cubic by the polynomial x minus 3. When you do that, you're going to end up with a quadratic, hopefully with no remainder. In the event that we messed up, we'd get a remainder. But we shouldn't get one if we divide x minus 3 into 2x cubed minus 3x squared minus 13x plus 12. Right? If you don't remember how to do this, you multiply x by whatever you need to get 2x cubed. So 2x cubed over x is 2x squared. And then you multiply this into here, and you get 2x cubed minus 6x squared. Subtract, and then keep going. Dot, 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 dot. Eventually, you should end up at 0. And what you get for your quotient is 2x squared plus 3x minus 4. And so the other two solutions to the equation are the two roots of this quadratic. I just need to use quadratic formula. So x equals negative 3 plus or minus the square root of 3 squared minus 4, a, which is 2, c, which is negative 4, divided by 2a, which is also 4. This simplifies to negative 3 plus or minus the square root of 41 over 4. And the question asks for the sum of a, b, and c, the sum of these three numbers. Negative 3 plus 41 plus 4 equals 42. Fortunately for us, that's one of our answers. All right, we're down to the last two questions here. Question 19. If a circle is inscribed in a square, the regions between them are each concave. If a square is inscribed in a circle, the regions between them are each convex. Suppose, and I'm going to do a very careful job of drawing this because this can get nasty really quickly. Suppose a circle is inscribed in a square, and then a square is inscribed in that circle, and then a circle is inscribed in that square, and then a square is inscribed in that circle, and so on, and it goes and goes and goes and goes and goes. What is the ratio of the total area of the concave regions divided by the total area of the convex region. So concave divided by convex. All right, so we start with a circle inscribed in a square. All right, let's go ahead and do that. I'm gonna make it really big. We're gonna have a square that I square, you know, I'm just gonna use, I have shapes. I can just do shapes. Square. I don't want to type anything into there. So we have a square. And a circle is inscribed in that square. More or less. That's my circle in the square. All right. The concave regions, when a circle is inscribed in a square, the regions between them are each concave. The concave regions are the blue regions right here. Now, the way I handled this, because I knew the numbers were going to be nice, it doesn't really matter how big these squares and circles are. The answer should be the same. The problem says nothing about how big the circle and square are, so we can start with whatever we want. Right? And so I knew the numbers would end up kind of nice if I started with a side length of 2. Right? And the reason is the radius of the circle is going to be half of the side length, so the radius is 1. So the area of the square is 2 squared, which is 4. Right? So the square gives me an area of 4, but the circle gives me an area of pi. Right? So the blue region, which I'm making this sparkly purple thing, so the 4 concave regions are going to give me 4 minus pi. The area of the square minus the area of the circle. Okay. That's the area of this first blue region. In fact, I'm going to, down here, call this A1, capital A. This is 4 minus pi. All right, so A1 is all of these guys. Scroll up a bit here. All right, that's A1. It's 4 minus pi. And now I need to inscribe a square into the circle. No, bad. Stop. All right, I'll make it nice to me. Inscribe a square into the circle. Not perfect, but honestly not bad. And the convex regions are the red regions. All right, the red regions here. And so I'm going to call these small a1. And ultimately, we're going to do big A over small a when we finish this problem. So remember, the radius of this circle was 1. So this right here is 1. That radius is 1. We can find the side length of the square. Actually, easier way to do that. We can find the side length of the square by doing this. That's 1, that's 1. This is a right angle right here. Those both go off at 45-degree angles respectively, so that's going to form a 90-degree angle. That's 1, 1, which makes this the square root of 2. And the area of the square becomes 2. So the area of that big square becomes 2. That means that A1, little a1, is the area of the circle, which is pi, minus the area of the smaller square, which is 2. All right, here's the issue. We're not done yet because we need to do this forever. We need to do this infinitely. But there's some nice logic that we can do. I'm not going to do it as logical as I am going to do it using a geometric series. So here's the next circle. I promise it's a circle. I'm going to call this A2. Remember that this side length of this square right here, this was the square root of 2. And so the area or the radius of this circle is half that. It's the square root of 2 over 2. And so the area of this circle is pi times that squared, which is actually pi over 2. It's pi halves. And so A2 is 2 minus pi over 2. What do we notice about this? We notice that this is exactly a half of 4 minus pi. And so a nice pattern emerges. We're going to go one step further to really nail down this pattern. But a nice little pattern emerges. So let's make the next square. Next square is going to be right about, I mean, it's looking more and more rectangular as I go, but I promise it's a square. Here's little A2. Remember, the radius of the circle is root 2 over 2. That means this is root 2 over 2. And so is this. Turns out, you use Pythagorean theorem, that actually gives you 1 for this side length. And the area becomes 1. And so A2 is the area of the smaller circle, which was pi over 2, minus 1. Notice, this is 1/2 of pi minus 2. So what happens? As we keep going, I don't need the picture anymore. As we keep going, A3, you're going to multiply by 1/2 again. You get 1/4 of 4 minus pi. And little A3 is 1/4 of pi minus 2. Keep going. A4 is 1/8 of 4 minus pi. Little A4 is 1/8 of pi minus 2. What we're interested in is the sum of all the big A's divided by the sum of all the little a's. I'm just going to call this big A. It's the sum of all these guys forever. This is going to be 4 minus pi, and then 1 plus 1/2 plus 1/4 plus 1/8, etc. And little a is going to be pi minus 2 times 1 plus 1/2 plus 1/4 plus 1/8, etc. When you divide big A minus, or divided by little a, you get that these expressions, the 1 plus 1/2 plus 1/4 plus 1/8, cancel. And you're left with 4 minus pi divided by pi minus 2. Oops. Sorry, got excited there. 4 minus pi and pi minus 2. Is that one of our answers? I sure hope so. 4 minus pi divided by pi minus 2. Last question. Question 20. In the diagram below, each variable p through x represents a different integer from 1 to 9. The operations, for which this right here is division, in each row perform left to right, and in each column from top to bottom, not using order of operations, result in the numbers at the end of each row and the bottom of each column. Find the value of p plus t plus x. All right, so a weird thing about this grid is that we're not using order of operations. We are just reading it from top to bottom or from left to right. So for example, if I look at this column right here, I'm going to do p plus s first and then multiply by v to get 77. All right, so that's how this works. And precisely, we are going to start there. All right. If I look at p plus s times v equals 77, this times v is really interesting to me. The reason it's interesting to me is because I need that v needs to be a factor of 77. Otherwise, I can't multiply to get 77. Well, 77 doesn't have that many factors. It's got 1, it's got 7, it's got 11, and it's got 77. These numbers are 1 through 9, so it's definitely not going to be 11 or 77. And if it's 1, then p plus s has to be 77. It can't be that big if you're adding up two single-digit numbers. That tells me v is 7. 7. All right, v is 7. Nice. Okay. So we can keep going and do similar sort of logic here. All right. I'm going to look now at this row. S plus t divided by u. Right. If u could theoretically be anything. But let's suppose that it was 2. If u is 2, then s plus t would have to be 24. That's too big. You can't add two single-digit numbers and get 24. If u is 3, it goes to 36. That's too big. If u is 4, it goes to 48. That's way too big. Turns out that 2 is simply too large, and all the other ones are too large as well. U's got to be 1. U has to be 1. I'm going to keep a list of numbers here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to check them off as we use them. So we've used 1 and we used 7. All right. So let's now look at this column here. R plus 1 times x. I know the times and the x look similar. I didn't like it how it was written on the thing, but that's how it was. R plus 1 times x equals 60. 60 is pretty big, right? 60 has a lot of factors, but, you know, it's pretty big. You gotta take those factors with a grain of salt. So we have what? We have 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 times 12, and 6 times 10. Those are the factor pairs of 60. Right? Obviously, x is a single number, so x has to be one of these numbers, either 1, 2, 3, 4, 5, or 6. That doesn't reduce much, except r plus 1 then has to be on the right side. And if r plus 1 has to be a 2-digit number, the only way you're going to get there is if r is equal to 9. If r is equal to 9, that gives you 10. That's as big as you get. You can't get any bigger than that. Which makes this 6. And we are now cooking because we have a lot of things that we can just rattle off now. For example, if you look at this horizontal row, right, you're multiplying by 6. That means 7 minus w has to be 5. W has to be 2. Right. So you get 7 minus 2 is 5 times 6 is 30. All right. So we've used 2. All we have left now are 3, 4, 5, and 8 to fill in this top left. Well, if we go back to the middle row, we know that the middle row, that s plus t, because you're dividing by 1, s plus t has to be 12. Right? We know s plus t has to be 12. There's only two numbers on here that add to 12. That's 4 and 8. So s and t are 4 and 8, but we don't know which one. Well, s and t are 4 and 8. We don't know which one. Let's use this one. We know p plus s has to be 11. There are only two numbers on here that add up to 11. That's 8 and 3. 8 is the one in common. So s has to be 8. P has to be 3. T has to be 4. And by process of elimination, Q has to be 5. And you can verify that all of these work. 3 plus 5 plus 9 is 17, going horizontally. 3, 5, 9 makes 17. 8 plus 4 is 12. Divided by 1 is 12. 7 minus 2 is 5 times 6 is 30. All the rows are good. Looking at the columns, 3 plus 8 is 11 times 7 is 77. 5 minus 4 is 1 times 2 is 2. 9 plus 1 is 10 times 6 is 60. We are good to go. P, T, and X, I blanked them out, but that was actually the diagonal. And so we are looking at 3 plus 4 plus 6, which is 13. That is the last problem. That is all 20 answers. And so that is it for the AMATYC Fall 2024 contest.